Okay, good afternoon. Friday, last day. I've got an attendance register as usual. As we're going along, if you want to look at anything in more detail, the book, Denny Jones, Corrosion, Principles and Prevention, is in the library, easy read. I've also discovered that not that you'll need them this semester, they're for next semester, but the past exam papers weren't on the blackboard. So there's an administrator looking into that so that you can see what the past papers look like, which will help you as we're going along. Okay, so a little bit more information coming along, but I would leave it all till semester 2. Okay, you've got more important things to concentrate on coming up in January. This is a summer issue. Okay. To add to that, I suppose I should also say that because we're not in an urgent rush to get through all the material in semester 1 in time for the exams, I will not be teaching the last Friday of term before the holiday, and I don't intend to do anything during that first week when you come back in January, just immediately before the exams. Okay, so I want to give you a clear run at your semester 1 exams. We're just going to stop, so we've got this week and next week, I think it is, and then the last week of term I won't be doing the Friday, and that week in January I won't be doing the Friday. I can put it on an email if you like, but you know, we've got more slots than we actually need to cover everything anyway. Okay. If you remember, we were talking about modes of corrosion, and we'd started looking at localized corrosion because that's a very significant proportion of the failures that occur, and we'd looked at pitting corrosion with the water droplet as an example on a surface, but also where you get a protective coating that is damaged, and then all the current, the anodic current, is concentrated in one location. And I showed you some samples of materials that had pitted, both pitting from the outside of the pipe in over and from the inside of the pipe out over. And what we found was that these modes of corrosion are strongly influenced by the availability of oxygen for the cathode reaction. So areas that are low in oxygen become anodes, areas that are high in oxygen become cathodes. And after a little bit of initial random anode and cathode production on your steel, they will migrate to areas of high oxygen concentration for the cathodes and low oxygen concentration for the anodes. So inside a crevice, inside a capillary, then that's a low oxygen area, and that would be an anode. What we're going to do now is move on. We're going to say a couple more things about crevice, and then we're going to move on and look at flow as a function of corrosion, and we'll look at erosion, corrosion, and cavitation corrosion. But there were a couple more things I just wanted to say about crevice. This is one of them. You don't need the details particularly. Just want you to think about what's going on. Anywhere where you build in a crevice into your geometry of your components, then that's bad news. So overlapping plates riveted together historically in structures was bad news. The answer, of course, is start welding things and put a fillet weld in to join the plates if they're going to be in an overlapped position. More likely it's going to be a butt weld, and that is a butt weld at the bottom here. And the thing you have to be a little bit careful about with welds is that the root of the weld is of good quality. What we've got here is a little crevice being generated because there has been insufficient heat in the welding process, and you haven't got good weld penetration of the joint. And of course in your pipes not only do you have the axial weld, you've also got circumferential welds where you're joining along. So your pipe has got a weld, through wall weld, and it's also where you join one pipe to another, you've then got another weld right round the end to the next pipe. Yeah. So the penetration of those welds is a very important business, so you don't end up with defects that might give you preferential attack due to oxygen differential. Okay. Let's just switch over. So that was the crevice corrosion. There's the oxygen reaction at the cathode, using up oxygen, and new oxygen has to diffuse to the cathode, and it has trouble diffusing along a long path. So if you've got a crevice, diffusing it all the way into the crevice is quite difficult. So the cathode reactions come out to the high oxygen area instead. Oxygen differential, and this drives the pitting corrosion, crevice corrosion, stress corrosion. It drives a lot of corrosion mechanisms. You had that last time. Don't think you've seen this one. Again, I'm not going to worry about the details, but the principle is quite interesting. The atmosphere is about 20% oxygen. The seawater at the interface near the atmosphere is about 8 parts per million oxygen. And so there's quite a big oxygen difference. As you get lower down in the seawater, the oxygen concentration is falling slightly, and the magnitude of any differences, because we're looking for oxygen differential, gets smaller. And so the bulk of the corrosion, this is corrosion rate in microns, 10 to the minus 6 per year. The bulk of the corrosion occurs near the surface because of that interface between a high oxygen area and a low oxygen area. So it's oxygen differential that drives the corrosion processes.
With accelerated low water corrosion, is that just because it's wetter for longer while still having the oxygen?
Sorry, could you...
Accelerated low water corrosion?
Accelerated?
Quite often steel pylons will rust through at spring low tide level, being low water springs.
Right. So that'll be oxygen differential again. There's a tendency to forget about, as we had in our earlier slides about classification of corrosion sites, mists and fogs and splashed water will still cause corrosion. So you're still going to get corrosion in the tidal zone. Yeah. And it's that water droplet, if you like, on the bit of steel with the large oxygen differential across it will give you the pit.
I mean, this is areas of a steel pile that would only be exposed for an hour or two every 2 weeks. Right in the bottom of the pile.
So these are pylons in seawater, and they corrode off at the bottom.
Just at the spring mean low water spring level.
Mean low water spring level.
So they're showing the maximum corrosion above the high tide level, where it's permanently exposed to atmosphere plus whatever electrolyte.
Yeah, and you're saying you're getting more corrosion at the low tide.
Typically, yeah.
Right. Don't know why that is. Pylons are rather unusual things in that they are coated in a rather good quality zinc containing paint.
Just normal piles, tubular piles.
Sorry, I thought you said pylon. Driven piles, so the flat plates with interlocking.
Just tubular, just like that. Just a bit of tube driven down.
Right. The only other reason I can think of why the load tide value might be higher than the value indicated here is the addition of the microbial action. Okay, so once you've got the marine wildlife attacking the structure as well, yeah, the corrosion rate will be different. Okay, so, and in fact, later on in semester 2, we'll talk about microbial corrosion. Sorry, I'm very happy to have questions. I'm a bit slow answering some of them because I do theory, not application. So if I wasn't picking it up very quickly what you were talking about, but I've got it now. And I think the difference is essentially what else is happening in the marine environment. Okay, but in terms of oxygen, the highest corrosion is going to occur near the surface interface. And of course that's very bad news for shipping, it's bad news for offshore structures, such as for oil exploration and so on. Okay. What I want to talk to you a little bit about now is how flow affects corrosion. And we've already said that the corrosion process is about an interface between a solid material and some solution. So everything happens at the surface. If you can flow new reactants into that surface and wash corrosion products away from that surface, then the corrosion gets faster. And that's because you've overridden the diffusion processes. So before, in the water droplet, for instance, we were having to diffuse oxygen through the solution, the stagnant solution, and that's a fixed law of diffusion if you're interested in the maths behind it. And it takes time for the oxygen to diffuse through the solution. Flow the solution, you're mechanically moving the oxygen along straight to the electrode. So the corrosion is going to be faster. And that's indeed what you find. So this is corrosion rate against velocity, meters per second at the top. I don't expect you to remember the numbers at all. Just the general concept that as the flow rate increases, and this is laminar flow, that is to say there's no turbulence, bubbles or anything like that in the flow. There's no particles in this flow. Okay, it's just nice clean water flowing steadily past the surface. So you get a speeding up of the corrosion, and that's because the corrosion is all a surface process. Actually, I brought you something along while I think about it. This just is a nice sample to remind people that it's a surface process that's important, the surface condition of your electrode, that's important. This is a small anode from a cathode protection system, and we've sliced the end off it just to show that it is actually a piece of steel. So it's the surface coating, obviously when the end isn't cut off, that's in contact with the environment, and that's an unreactive material. It's actually a titanium compound. That allows you to use it as an anode without it dissolving away, but the centre of it's actually a piece of steel, a piece of mild steel. And the reason is all the electrochemistry happens at the surface. It doesn't matter what the interior looks like as long as it isn't in contact with the surface, with the solution. Yeah. So that's a little anode from a CP system. We'll come back to CP systems later on. Okay. Exactly how the corrosion rate increases with velocity varies a little bit depending on the environment, and I've got another plot to illustrate what happens as the flow changes. Place that this time. It's not helping, is it? Okay, so again it's corrosion rate, but this time not just the laminar flow region. We've added turbulent flow, in other words the velocity getting even higher, and then finally cavitation. And what you find is that under laminar flow conditions the corrosion rate increases gradually, and then once you go to turbulent flow the corrosion rate increases rather more significantly. And then when you go to cavitation, the damage becomes accelerating very rapidly. So what's happening here, what we're getting is, under laminar flow conditions, you're just getting the chemical corrosion, the electrochemical attack. As the velocity goes up, you're now introducing a mechanical component to the attack, to the damage. So you're getting a combination of corrosion and a turbulent flow erosion, which we're going to talk about in a minute. If the velocity gets very fast, then the failure is mechanically dominated. So at low velocities it's corrosion dominated, at high velocities it's mechanically dominated, and then you've got a spectrum of conditions in between: corrosion dominated, mechanical dominated. Okay. So where we're going now is into this area here to look at turbulent flow, erosion, and then cavitation. Yes, sir.
For what I'm reading, I think that this kind of corrosion might be especially present in stainless steel, in the inner tubes of stainless steel. Is that correct?
Yeah. Alloys that passivate are more susceptible to the corrosion part of the mechanism. Yeah. It's a bit like the river or stream running over the rocks. There's a mechanical component wearing away the material just from the flow, and then there's the corrosion attack, which is the pitting in combination with it. So it is does occur in stainless steels, but it occurs in quite a lot of flow systems and in a whole range of alloys. The image you've got there on the screen is actually a pipe bend, and the fluid has been flowing round that corner on the inside of the pipe and has worn away the outer radius of that pipe. I should say that the graph you had on before of the corrosion rate against fluid velocity, that's for a solution without any particles. It's not got suspended sand in it or bubbles in it, because they even they accelerate the attack even more. So you can imagine it's a bit like shot blasting the surface if you've got sand in the solution. So wherever you get some turbulence in your flow, and you may not have deliberately designed your system so that the fluid flow is turbulent, so you might have laminar flow in your pipe, but as soon as you hit an obstruction, a bit of sludge or debris on your pipe, then you can convert that into turbulent flow. Similarly, you get what they call impingement on pipe bends, and these are the sort of places that you start getting problems. In your pipe network, of course, you've got welded joints between two pipes, and we were looking at the root of the weld before. If the root of the weld is sticking out on the inside diameter of the pipe, yeah, there's a converse one here. If the root of the weld is sticking out, then as the flow comes round, it's got a flow and it'll impinge. So these impingement sites are important to consider, and that means the quality of your fabrication in terms of getting good root penetration, but not so much weld material that you've got loads of bumps on the inside of this pipe every time you've got a joint, is quite important. Okay. So that's erosion corrosion, combination of corrosion and mechanical impingement of the solution on the surface. After that part of the velocity corrosion flow, we go on from erosion corrosion at even higher velocities to get cavitation corrosion, and we'll look at that in a second. What I've got here is two samples for you to have a look at. These are test rig samples from what they call a flow loop. So there are people who spend their entire lives flowing solutions past bits of metal. Okay, this is a copper alloy. There's one sample which is, if you look through the centre of it, you'll see it's smooth bored. That's a blank. It hasn't been tested yet. Okay. The other one is a tested sample, so you can get a comparison between the two. And if you look down the bore of that, you'll see that there is a ripple finish to the surface, very like the bottom of a stream bed. You know, where the sand just has that sort of ripple in it. It's the same sort of effect, but you get it on the surface of the metals when you've got erosion corrosion going on. Okay. So they're just for comparison. courtesy of one of my colleagues who has retired now, but he spent, good 30 years working on flow. But that's another story. Right. So, if the velocity gets even higher than required to generate turbulent flow, you start getting cavitation. Where does this happen? Well, it happens in systems that are being pushed very hard, so propeller systems, pumps, those sort of situations. All right. So if you over rev, if you turn a propeller or impeller too quickly on the in a fluid, then you'll begin to get shear between the solid rotor and the liquid, and the shear velocity is enough for void formation to occur in the solution. So these aren't gas bubbles forming, these are holes forming in the solution because the blade is cutting past it so fast. And those voids are unstable and they collapse explosively. So you've got a void and it goes, yeah. And that provides the mechanical impact on the metal surface, and therefore it provides the mechanical extra to the corrosion to give you cavitation corrosion. This photograph here is a high-speed camera image of a prototype ship's propeller being photographed so they can actually locate the quantity and number of the shear voids being generated on the surface. So that's the sort of thing that would be done in that Emerson cavitation tunnel that they've just been stripping out of marine technology. The bottom photograph is a photograph of a corroded ship's propeller. You can tell from its bluey-green tint that it is a bronze alloy, or at least a copper alloy. It'd be bronze though. Most marine copper alloys are bronze. And it would have had a perfectly smooth, flat surface, but there's been quite a lot of damage there. There's more damage out at the edge of the propeller than there is near the centre of the shaft, because the radial velocity is so much higher on the outer edge. What you quite often find, and it's not very clear on this one, is that the leading edge, if the propeller's turning that way, might be going the other way, I don't know, but whichever is the leading edge of the blade tends to get more damage than the back end of the blade. But so this is a problem, and again, once you've got other things in the solution, particles, solid particles, and so on, then it can be worse. And it happens in lots of pumping situations, not just ships' propellers, but the impellers in pumps, because people are always trying to get more fluid down the pipe in a short length of time to make more profit, and that means pushing your pumping system, and not always a good idea. It depends how clean the material is you're pumping, the liquid you're pumping, and what the pipework looks like in terms of the quality of the interior surface finish and the number of bends in it and so on. Okay. This is a photograph of a ship entering New York Harbour in 1935. It's the SS Normandy. Why am I showing you this? In that sort of era, the only way to get to America was by ship. Okay, no passenger aircraft, and all the nations were competing to have the fastest transport route across to America. The British, the Italians, the Germans, you name them, they built luxury liners and raced across America. This is Formula One of the 1930s, okay? Really is. So, this particular ship, and the competition was for a thing called the Blue Ribbon. So, the Blue Ribbon for the fastest crossing of the Atlantic. That's what they were all competing for. This particular ship doesn't look anything very much in terms of photograph until you look at the skyscrapers behind it. You realise just how big it is. It is about 300 metres long. It's 80,000 tonnes of steel work and fittings. The engine's 180,000 horsepower. Okay, diesel electrics, enormous amount of power. This was built for prestige. This was built for racing. Okay. And sure enough, in 1935, it won the Blue Ribbon for the crossing of the Atlantic. Excellent. Unfortunately, the various other people were competing and various other nations took turns for it. But you got a lot of extra trade by winning this race. This is the leading edge of one of the propellers off that ship that made the fastest crossing in 1935. Please don't drop it. So it's a phosphor bronze, it's an adamantry bronze propeller. That's just one leading edge. So the blade is cutting through the water. It would normally be a smooth, polished, beautiful, sharp-edged. It would almost have a razor edge on the front of it. And you can see it's all been eaten away. Why is that in the UK? Well, the race was between New York and Southampton. And what you did was just like Formula One. you went round the track a couple of times, or maybe just once, and then you dropped the propellers and you put a new set on, and you went for it again, because they were cavitating them all the time. In fact, sometimes they cavitated while they were partway across, and that was very embarrassing, because there were descriptions from the engine rooms of the whole place vibrating, you know, because the propeller was out of balance, because a bit of it had dropped off on the way, and the whole thing was almost shaking to bits. The passengers in first class didn't notice very much, but the boiler men wrote it all down. And so you dropped the propellers and turned around and did the race back again. So there are actually quite a few of these. They're not as rare as it might first appeared, but that one is quite nice because it relates to a win at that time. What sort of speed were they going? If you want to be nautical, about 30 knots. If you want to be land-based, 35 miles per hour. Not bad for a thing that big. Was the average speed, and to do that, the rotors were rotating at an average of 234 revs per minute. So, any rate, obviously, if you weren't racing, you wouldn't expect to replace your propellers. You would go a bit more slowly, and you'd expect them to last about 100 trips, something like that. But because they were racing and they knew they would get more clients by putting the foot down, they were burning the propellers off on one crossing, you know. So there you go. That's erosion, cavitation corrosion at its worst.
So this ship now is discarded?
Yes, sadly, it was just after the Second War. It was sent to, I think it went to Bremen to be stripped. So not there any longer. But right, modes of corrosion. What I want to do next is talk to you about the combination. Actually, let's just check that's right. Yes. So on your handout at the bottom, you've got what's entitled environmentally induced cracking. Sometimes it's called assisted cracking. So it rather depends on whether the cracking wouldn't have occurred without the environment, or whether the environment just helped it crack. Depends on your viewpoint. So environmentally assisted or environmentally induced cracking. And there are in the title, the word corrosion isn't present. Why is that? And that is because this third mode, this one at the bottom end here, which we'll talk about later, hydrogen cracking, it's got nothing to do with corrosion. It's not a corrosion mechanism. It is electrochemical in some situations, but not anodic corrosion. The other two both follow our oxygen differential rule that we talked about earlier on. So these are corrosion processes. You get anodes forming at low oxygen inside the capillary. So this is where the corrosion occurs, at the cracked tips. And you get cathodes forming where there's loads of oxygen on the outside of the structure. Okay, so it's just like crevice. It's the same sort of thing. The difference from crevice is that there is some loading present. And what's you're short of perhaps on this diagram is where the stress is, where's the load on the structure. And the load is always so the stress is at right angles to the crack growth direction. So if the crack's growing that way, the stress is horizontal. And you can add that to your diagram if you want. So the stress is going that way. In corrosion fatigue, it's still stressed that way, but it's cyclic loading. Whereas you've got static loading here, you've got cyclic loading under fatigue conditions. So the stress is on and off, on and off. Yeah. hydrogen-induced cracking, the stress is still at right angles to the crack growth. So the reason why the hydrogen embrittlement is or hydrogen-induced cracking, as it's sometimes called, is in the same batch is because they all have this one thing in common. The crack grows at right angles to the loading direction. But otherwise, the first two are anodic corrosion processes, and the third one isn't. Okay. So, what we're going to do is start off talking about stress corrosion cracking. And then we'll talk about corrosion fatigue and then hydrogen embrittlement. So we'll work our way through those. And the first thing to say is this stress that we've got on the material can be from more than one source. Oops. So you don't need the list at the bottom. That's on your. You've mentioned corrosion fatigue. You've got hydrogen embrittlement. The stress. Let's do the stress first. The stress can either be residual in the material, or it can be applied when you're using the material in your component. And the thing that is significant is that the material may fail at stresses way below the yield strength of the material. The cracks you get can be of two forms. They're either intergranular, they go between the cracks, and then the crack often has a shape to it, so it's going round the cracks, the grains in the material, or transgranular, and it looks fairly straight. So this is IG, and that's TG. So your anode is the crack tip. Okay, so this is the anode. The cathode is somewhere on the near the outside, because that's where the high oxygen value is. And then the action of the stress is to keep pulling the material apart at the crack tip. Because the material will fail below its yield strength, it means all the finite element analysis and all the design preparation that somebody's done in a drawing office somewhere is out the window. Okay. If they haven't allowed for the environment, the material will fail, even though it shouldn't do below its yield strength, it will do. Actually, that's always a good question. I'll ask you the question to see whether, as engineers, you've got the answer. So, what is the maximum residual stress you can get in a material? What is the what is the maximum? No, what is the maximum residual stress you can get in a material? Okay, so the answer is sigma yield. Okay, that's the maximum stress, and even if you exceed that, the material will then distort and go to that value. So, and that's why when you look at large plate structures like ships, the panels are slightly curved. If you look at the where they've been welded around the edge, so they were flat to start with, welded around the edge. The material is distorted because the residual stresses were greater than the yield strength until it's down to the yield strength, and then it stops. So you end up with these slightly curved plates on the hull of the ship. Okay. So there are a lot of components that are sitting just below yield strength after fabrication. So there are a lot of components that will be susceptible to environment-assisted cracking in the right environment or the wrong environment, depending on how you look at it. Okay, so it's a very significant cause of failure. What we're going to do next time is look at some examples of the failures. We'll talk about stress corrosion cracking in pipelines, and work on from there through to corrosion fatigue and hydrogen. Thank you. Hi, all right?
Yeah. I finished reading one of the dissertations you did.
Oh yeah, yeah. Any good?
Yeah, I like it, but I think that this is only the experimental approach, isn't it?
Yeah.
And you said that it would be good if I made like a theoretical model, so I compare them, both of them. So I'd like to know how that's gonna work, like how the model should be like derived from the equations and then tested, or what kind of model?
Now then, remind me what the...
Oh, the hydrogen brittle.
So this is hydrogen.
Yeah, sorry.
So, yeah, I talked to a guy, one of my colleagues, who is a modeler. Yeah, and he has a model for diffusion of absorbed hydrogen into steel, which needs some development and work.
Oh, okay.
So it's sort of related to that fixed law of diffusion and things, but a bit more complicated. So he said he would be interested in doing a sort of joint exercise.
Yeah.
Yeah, I could probably just wondering whether I can get a sample of the model from him, or whether it'd be better for you to go and talk to him about the modelling side of it, or whether the three of us should meet together. What do you do next week?
Ooh, that's a good question. Yeah, I think. Yeah. Just give me a second.
Yeah.
But
Well, that's loading up. Shall I do another one? Who's next?
I was just wondering if you could send an email out about which sessions were going to be cancelled.
All right. Yeah.
Because they're
It's
driving
the
from
last
just-
one, the Friday, just before Christmas, which is the 16th,
All right.
and the January 9th, is it? No, 9th, 10th, 11th, 12th, 13th. Okay, because there's no point doing
Right.
one. That's really your revision time for the exams in Jan. Yeah.
All right.
Okay.
Okay.
Yeah.
Yeah,
Great.
thanks.
Cheers.
Yeah, what is that? I just wanted to say hi. I'm going to drop you an email so that I can start working on the proposal.
Okay. Yeah. Good. Yes.
Am I allowed to speak with the technician so that they can just pull me through so I can understand the way I will structure my methodology? Am I
They
allowed?
probably won't be able to help you.
Okay, so
maybe
I can
not.
Just read and.
If you want to do a draft, and I'll give you some feedback. How does that sound?
Okay, I should send you the draft,
Yeah.
right? All right.
Yeah. Thank you. Cheers.
yeah, I'm pretty much free next week. Yeah,
Oh, that's
so,
nice.
Yeah.
I want a job like yours. How about? Well, I don't know whether
From
Dr. Doyle is
Monday
available.
to Wednesday, I'm very free.
Let's say 2 o'clock on Monday, shall we?
Yeah.
But I'll have to check whether Dr. Doyle is free or not.
Okay. Yeah, and about the kind of steel I like to taste, I think that I like to focus more on onshore pipes, so that would be around X60, 65 because are the more common. And I noticed that in the dissertation I was reading, they use like high strength pipelines. So is there like a significant change?
They're quite different materials, but we're interested at the moment. We're interested in the higher grades because they're the ones being developed. But if you want to do an applied one, I don't have a problem. Or actually, the best thing to do is to do a comparison between
the lower and the high strength.
Yeah, and then you find a difference in something. Can I just get your name off here so I can,
also
then I'll send you an
another
email.
Question, what I know in the list,
That's your
like
email.
this is the second time like I got the.
Yeah, I've just got it from new contacts and maybe it's out of date.
Okay,
I'll
that's all right.
I'll try and get another copy of it.
Yeah, that's all right.
I'm sure you're supposed to be on the course.
Yeah, it's in my timetables.
Right. That's grand. So hopefully I'll see you on Monday, but I'll drop you a note. See what Dr. Doyle has got to say.
I know you were.
Oh, we can be a gang. Go all the way back.
No, she made us come to the front. I thought she should.